This presentation introduces a scientific article, a novel capsule neural network based model for drowsiness detection using electroencephalography signals. Authors. This article has an international team of authors. These are employees of universities and laboratories from Chile, Germany, and Brazil. The detection of drowsiness is currently one of the most relevant challenges to guarantee safety and reliability in several industry sectors. As an example, in the incidents of 3 Mile Island and Chernobyl, drowsiness was documented as a contributing factor. The greatest risk, of course, is falling asleep while driving. In trains and planes, traffic is still controlled by automation, and even a few seconds of sleep on a busy highway can be fatal. Due to the transient mental state of a human subject between alertness and drowsiness, automated drowsiness detection is a complex problem to tackle. Although the methods of eye tracking have achieved good results, the use of video devices makes these techniques too invasive for operators' privacy. The EEG signals can be divided into 4 segments depending on their frequency band. Each of these bands refers to different states of consciousness such as sleep, intense mental activity, and drowsiness. This scale measures the level of self-perceived sleepiness for the individual in the last 10 minutes. Karolinska Sleepiness Scale has 9 gradations from extremely alert to extremely sleepy, fighting sleep. Convolutional neural networks, CNN, are deep learning algorithms developed to tackle matrix data such as images. CNN are composed of 3 types of layers: convolution layer, pooling layer, and classification layer. The generic architecture of CapsNet is composed by the following layers: input layer, convolutional layer, primary capsules, secondary capsules, and finally the output. Hinton and Sabu explain that the brain is organized into modules, which can be considered capsules. With this in mind, they proposed capsule networks which incorporate dynamic routing algorithms to estimate features of objects like position, size, orientation, deformation, velocity, texture, and so on. Like normal neurons, capsules perform their computation on their inputs and then encapsulate the results into a small vector of highly informative outputs. A capsule could be considered a replacement or substitute for your average artificial neuron, whereas an artificial neuron deals with scalars, a capsule deals with vectors. In this study, only the EEG signals and KSS scores of the subjects were used. From the 5 EEG channels available for each subject, only the signals recorded by the frontal and parietal electrodes were used. This choice is based on the fact that alpha and theta waves show an increase of amplitude that can be measured in mentioned channels in case of the subjects is in the drowsy state. The database was collected from 14 completely healthy young subjects who were subjected to 3 psychomotor vigilance tests of 10 minutes duration, where the subjects had to monitor a red rectangular box over a black background on a computer screen, and to press a button as soon as a yellow figure appeared inside the red rectangle. To ensure the drowsy state of the subjects, they were induced into prolonged waking state during the tests. As it can be seen, the proposed CapsNet model reaches better average results than CNN for both datasets for all the performance metrics. Indeed, CapsNet reached 84.45% of accuracy for the frontal dataset and 86.74% for the frontal parietal dataset, versus the 79.46% and 75.86% reached by the CNN, respectively.